Alright, let's do some math, because I'm bored. Let's prove that lim x goes to 0 of sine x over x is equal to 0. And let's not do it in 1, 2, but 7 different ways. First way, graphing. Obviously, you can tell this limit is equal to 1.
That was easy.
Number 2, L'Hopital's rule. Number 3, the unit circle. I'm just going to draw the unit circle out like this. The origin is here, O, and it has a radius of 1. So this point P is 1, 0. Some point here, it could have any point here. R is equal to 1 there, R is equal to 1 here as well. You have 3 areas to worry about. This small triangle here, this sector, which is this pizza pie slice, and this vertical tangent line formed by P that goes up to here. Let's call this point Q. Area of small triangle. The area of the small triangle is equal to 1/2 base times height. The base is just r equals 1, so it's just 1/2 times height, which is 1/2 sine x. The area of the sector is equal to 1/2 r squared x. R is just equal to 1, so this is 1/2 x. And the area of the big triangle that's 1/2 base times height. Again, the base is just r equals 1, so this is 1/2 times height, which is 1/2 times tan x. It's safe to say that when x is between 0 to pi over 2, you have sine x less than or equal to x less than or equal to tan x. Because geometrically, you can clearly see that the area of the small triangle is smaller than the area of the sector, which is smaller than the area of the big triangle. So this inequality has to be true. Divide all sides by sine x, and you get 1 is less than or equal to x over sine x, which is less than or equal to tan x divided by sine x is 1 over cos x. I'm just going to take the reciprocal of all 3 values, so what you end up with is cos x less than or equal to sine x over x less than or equal to 1. Let's take the limit as x goes to 0 on all 3 sides. So, therefore, by the squeeze theorem, the limit of x goes to 0 of sine x over x equals 1. The fourth way we can do it is through the Maclaurin series. The formula for the Maclaurin series is f of x is equal to a summation notation n equals 0 to infinity at the nth derivative of 0 x n over n factorial. So here we have f of x is equal to sine x, f prime of x is equal to cos x, f prime prime x is equal to negative sine x. The third derivative of f is negative cos x. And the fourth derivative is equal to sine x, which is just repeating from the original function. So this is a repeating of derivatives. F of 0 is equal to 0. F prime of 0 is equal to 1. F prime prime of 0 is equal to 0. Third derivative of 0 is equal to negative 1. And the fourth derivative, 0, is equal to 0. So we can establish a pattern based on what we saw right here. Therefore, we can say that sine x is equal to x over 1 factorial minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial. You get the idea. So, therefore, what we can say here is lim x goes to 0 of sine x over x equals lim x goes to 0 of x minus x cubed over 6 plus x5 over 120, so on and so forth, divided by x, which is then equal to lim x goes to 0 of 1 minus x squared over 6 plus x4 over 120 plus some other higher degrees of x. As x goes to 0, all of these values cancel out to 0, and you're just left with 1. So once again, our solution is correct. The next way is the mean value theorem, and here's a quick refresher of it. Let's say you have a point A right here, and let's say point B is right here somewhere. And you can draw a slope from A to B like this because f of x is differentiable from A to B and continuous from A to B. Imagine this is the slope from A to B. Then that means there exists some value C that's between A to B that's derivative is exactly the same as the slope from A to B. In mathematical notations, this is what the mean value theorem states. If f of x is continuous from A to B and differentiable from A to B, then f prime of c, there exists some c where f prime of c is equal to f of b minus f of a divided by b minus a. So I'm going to just quickly write this formula here, take a note of what the mean value theorem is. I'm going to erase everything but keep this formula. Let f of x equal to sine x. And we know sine x is differentiable, no, let's say continuous from 0 to some real value x and differentiable from open interval 0 to x. This means the mean value theorem applies, and we can say that f prime of c is equal to f of b minus f of a over b minus a. F prime of x is cos x, so f prime of c is cos c, some constant c, is equal to sine x minus sine 0 over x minus 0. Cos c is equal to sine x over x. Let's say that sine x looked something like this. 0x f of x is equal to sine x, and let's say c existed somewhere between 0 and x. What if we made c to be as close to 0 as possible? What would happen? Well, the limit as c goes to 0 of cos would equal the limit of x goes to 0 of sine x over x, which is just equal to 1. Number 6, complex values. This is kind of similar to the Maclaurin function that we did earlier, but let me just explain this. So, if you took linear algebra or complex variables, you would have learned that sine x is actually equal to e to the power of ix minus e to the power of negative ix divided by 2I. So this means that sine x over x is equal to e to the power of ix minus e to the power of negative ix divided by 2ix. Now, the Maclaurin function for e to the power of x is e to the power of x is equal to, from n equals 0 to infinity, of x to the power of n over n factorial. I'm not going to show you how I got this, but this is true. Yeah. From this, we can say that e to the power of ix is equal to the summation notation from n equals 0 to infinity of xi to the power of n over n factorial, which is equal to, if you just spell it out, it's 1 plus xi minus x squared over 2 minus x cubed I over 6 plus x4 over 24 plus x5I over 120, etc., etc. Similarly, e to the power of negative ix is equal to this notation, summation notation, n equals 0 to infinity of negative xi to the power of n over n factorial. This is equal to 1 minus xi minus x squared over 2 plus x cubed I over 6 plus x4 over 24 minus x5I over 120, etc., etc. So, therefore, lim x goes to 0 sine x over x is equal to lim x goes to 0 of e to the power of ix minus e to the power of negative ix over 2ix. This is equal to lim x tends to 0. When you subtract e to the power of ix minus e to the power of negative ix, you end up getting 2xi minus 2x cubed I over 6 plus 2x5I over 120 divided by 2xi. You can factor out a 2xi here, and you get lim x tends to 0 of 1 minus x cubed over 3 plus x5 over 120, ... All the other terms other than 1 will cancel out to 0, so you're left with a value of 1. Last but not least, we have the Delta-Epsilon Method. Let me give you a quick overview of what this method is. It's just the precise way of defining a limit. Suppose we found that the limit as x approaches a of f of x equals some value L. Then, for every epsilon greater than 0, no matter how small epsilon is, there exists a delta less than 0, some small delta, such that 0 less than absolute minus delta, 0 less than absolute x minus L, which is less than epsilon. It doesn't matter how small epsilon is, you will always find a corresponding delta. So basically, we need to find some explicit relationship between delta and epsilon. Once you do that, you're done the proof. I'll go over the Delta-Epsilon method in more depth in another video, but for now, let's just use this strategy. So we know that the limit as x goes to 0 of sine x over x is equal to 1. We know that L is equal to 1. This means that there exists 0 less than absolute value of x minus a, which is just absolute x, less than delta, and in turn we can find that 0 less than f of x is sine x over x minus 1 less than epsilon. Let's find a relationship between delta and epsilon based on these two pieces of information. So the first thing I'm going to do is I'm going to look at the absolute value of sine x over x minus 1. This is equal to absolute sine x minus x divided by x, because x over x is just equal to 1. Now, I'm not sure if you guys remember this, but the Maclaurin series for sine x is equal to x minus x cubed over 6 plus x5 over 120, dot, dot, dot. So sine x minus x is equal to negative x cubed over 6 plus x5 over 120, dot, dot, dot. Now, this is where things get interesting. If the absolute value of x is less than 1, then what we have here is the absolute value of x7 over 7 factorial is going to be less than the absolute value of x5 over 5 factorial, which is going to be less than absolute value of x cubed over 3 factorial. And why is this important? Well, let's say you took a number like x equals 0.5 here. Well, if you raise 0.5 to a higher power, its magnitude is going to decrease in size the higher the power 0.5 is raised to. So if the absolute value of x is less than 1, the higher the power is, the lower the value is going to be. So in turn, right here, the absolute value of sine x minus x, this means that this value is at most equal to the absolute value of x cubed over 6. It's no bigger than this value. So from this, we can say that the absolute value of sine x minus x divided by x is less than or equal to absolute value x squared over 6. And this is less than epsilon. So if we took delta to equal absolute x and epsilon to be x squared over 6, then our formula is delta is equal to min 1 root 6 epsilon. We've now established an explicit formula for delta and epsilon, but let's show that this is true. So, the proof that our formula is correct. absolute value sine x over x minus 1. Let's show that this can be less than epsilon using our delta formula. We showed that this is equal to absolute sine x minus x divided by x, and that this is less than or equal to absolute x squared over 6, and this is less than delta squared over 6. We know what this is equal to. This is equal to the square root of 6 epsilon squared over 6, which is in turn equal to epsilon. So we got it right. Our limit is correct.